Okay, so welcome everybody to this CFAR session on machine learning for epidemiological studies. So this is based, I think, on the voting that has been done for CFAR for topics of interest that happened to coincide nicely with a primer that Qifang Bi, my co-presenter, and myself, Justin Lessler, Catherine Goodman were all writing for AJE. So we, based on the interest, we decided to turn that primer into the presentation that we'll be giving you today. So a little bit, so I am a faculty associate professor in the Department of Epidemiology. But in a previous life, I was actually a computer scientist working at IBM, doing this kind of stuff for a living. So I know something about it, but it's all, a decade and a half out of date. But it's there somewhere. And Qifang is a PhD student in the department. So this is going to be a relatively high-level introduction to some of the major techniques and terminology and approaches that are used in machine learning. And machine learning is old, and it's part of a trend of, a lineage of concepts and ideas that have, go all the way back to the AI movement in the 1950s, arguably earlier, and has been known by names, or has had incarnations. These techniques have had incarnations in names and everything from data mining to artificial intelligence to knowledge management, but maybe that was only in IBM, I don't know. And in this type of approach, computers learn, they improve their performance at task through experience. And this is just another way of saying they fit through data. But the differences, the things that make something machine learning rather than statistics, I think, are, statistical are really probably twofold in most cases. One is just simply where people came up with it. Did engineers and Bell Labs come up with the idea, or did statisticians come up with the idea, right? And depending on where the idea or the approach was developed, it tends to carry the label with it. But also I think, machine learning techniques tend to reflect a more engineering style approach to validation and understanding stuff. It emphasizing predictive accuracy and just the stuff works or it doesn't, and not really having the same sort of focus on a strong theoretical grounding that statistical techniques would typically have. In another way to say, and in general, these techniques have over time emphasized predictive accuracy over hypothesis-driven inference. But we're in a resurgence, and part of the reason we're having this talk now is I think that there's been a resurgence in interest in AI and machine learning. It's been all over the news. Facebook's top AI scientist says it's dust without artificial intelligence, and that if you take the deep learning out of Facebook today, Facebook's dust. Or Google's DeepMind, which is the project that's led to AlphaGo. I don't know if anybody else follows computers beating people at games as much as I do, but the AlphaGo, this program and and its descendants that have beat the top computers at chess, beaten the top people at shogi, and computers at shogi beaten the top people at Go, and finally, first computer to ever be human at Go, are all based on this resurgence in AI and these ideas about deep learning or adversarial neural networks and stuff. Hopefully we can explain a little bit of what that is today. So we're going to go through sort of 4 big sections in this sort of primer of a presentation. We'll talk about a little bit about the ways machine learning algorithms are classified and the terminology that's used, because sometimes some of the confusion from reading that literature isn't so much that there's any different concepts or new concepts being presented that you might not be familiar with, it's that people use different language. We'll talk about 5 common machine learning algorithms. We'll talk about ensemble models, and then we'll talk about applications in epidemiological research in the health sciences. So to go through, the basic process that that machine learning algorithms all go through. Does this pointer work? It does. All right. So is that you have some data set and then it is fit, and sometimes in machine learning, instead of a model fitting out, what we would call a model fitting algorithm is called a learner. And you get some model that's that's often called a classifier or an estimator, and usually it's thought of as a black box. The parameters, as you'll see as we go through the specific algorithms, the parameters are not necessarily exposed to the outside world and visible to you in a meaningful manner. And then so that's a fitting task, and then there's a prediction task where the model is taken. We have some unlabeled data set or some data set where things are unknown. Here, we don't know if this person is likely diabetic. We shoot it through the model, and we get a prediction, a forecast. So going to this, that got a lot brighter. Coming to this idea of the data set and the way things are talked about in machine learning, let's introduce some new terminology. So, what we might call an independent variable or a covariate in the machine learning community is often talked about as an attribute, a feature, predictor, or field, or input. Attribute or feature is probably the most common way things are referred to. So these are features or just covariates. The output is what we'd call a dependent variable or outcome. The range of values of the inputs is the input domain. And then, the dependent variables, what's called dependent variables, or really anything that has a value associated with it, is usually called labeling, that these are labeled. And a lot of this comes from the idea of, a lot of this terminology comes from the idea that a lot of this stuff was developed for text classification and other classification problems where you'd have a group of grad students locked in some room somewhere that would be labeling some of the data observations that you were going to train the computer on. And then the number of covariates and stuff is referred to the dimensionality of a problem. And for those of you who are more statistical, this is not necessarily new, new terminology. Machine learning algorithms are, there's lots of ways they can be classified, but I think there's 3 big dimensions where things are usually classified. So there's supervised learning, what's called supervised learning, and what that means is that the outcome is known, is that the algorithm is given a series of labeled observations, i.e. observations with an output variable or with an outcome variable, and it's known and it learns from that, just like we're familiar with logistic regression, linear regression, and the like. In unsupervised learning, the outcome for each is unknown. So we're looking for patterns. We're trying to sort of get patterns from the data without knowing the outcome. And this is more like principal components analysis or other types of latent class analysis. Algorithms are either are termed either classification algorithms, and that's when there's a categorical outcome, often binary, or regression algorithms. And in the machine learning community, when they say regression, they mean continuous outcome. And then probably the most novel difference in the way people are used to thinking of stuff, and we're going to go through these in a little more detail, is discriminative algorithms. So algorithms that are just aimed at saying, okay, this is X and this is Y, versus generative algorithms, which are algorithms that actually retain some full data model and would be able to produce new data. And we'll go through these in a little bit more detail. So first, the supervised versus unsupervised. So right, in supervised learning, is our typical learning pipeline, right? Or fitting pipeline. We have some labeled data, we come through, we learn, we have our model fitting algorithm, we get our model, then we use that to classify new observations based on this known outcome. So in unsupervised learning, we have something, and it's not necessarily diabetic, that is completely unknown or unobserved, and we're trying to just pull out patterns from the data. And like in latent class analysis or like that, we're going to build some model that's trying to capture inherent patterns in the data, and then create some classes based on those. Okay, so classification versus regression is quite simply the outcome, right? In the classification algorithm, the outcome is something like, is somebody diabetic? Yes, no. We fit a model, it fills in that. It's a categorical outcome. Whereas the regression, the outcome is a continuous number. And it's of note that most of these algorithms, most of the algorithms in machine learning were originally developed for classification and but many of them have been adapted for the regression problem. And they tackle the regression problem in a way that's akin to classification. And then finally, the thing we want to talk about most here, because it's sort of the most new and subtle, is this discriminative versus generative description. So in a discriminative model, you want to directly model the probability of an outcome given the data. So for those of you who are more statistically minded, this is the equivalent of estimating the probability of y given x. So all we're doing is, if we have this data here, is we're just figuring out how to draw a line between them. And say, okay, things on this side over here, they are, class black, and things on this side over here, they're class gray, and all we're doing is dividing the line, and we're not creating a model of the data of enough sophistication that we could generate new data or example data. And this is contrast into a generative algorithms where we directly model the probability outcome y giving observed data of x by modeling the joint probability of the data. That is, we're modeling the probability of the covariates and the outcome together. For the statistically minded view, this is just a probability, modeling the probability of the joint distribution of x and y. And this allows us to generate new data representative of the population. So if we have a similar problem as before, where we have our two groups, and here we've mixed them up a bit, in a generative algorithm would be an algorithm where we actually fit maybe multivariate probability distribution to each of these groups. So that with those distributions, I could create sample data that was representative of each of these classes, hence the name generative. So those are the general categories that things are divided into, and a little bit of terminology. And now, Qifang is going to take us through some common machine learning algorithms and introduce them to us.
All right, so we are going to talk about 5 common machine learning algorithms, starting with decision tree, then naive Bayes, support vector machine, artificial neural network, and k-means clustering. So as Justin introduced, there are different ways of characterizing different algorithms. So the 4 on the left side are supervised methods, and k-means clustering is unsupervised methods. Almost all of them can be used for regression and classification purpose. Let's talk about decision tree first. So decision tree is a supervised learning method. It's also a discriminative algorithm. So just a general overview. So decision tree is a series of decision rules that partition data into 2 or more groups, but it's usually 2. And then each partition creates groups that fulfill some sort of, some measure of data purity. And the process terminates when further improvements are not possible or some kind of pre-specified criteria is met. And the terminal nodes on the bottom of the tree would assign a class probability or a value depending on if you're doing a classification problem or regression problem based on membership of the final partition. Okay, so this is a lot. So I just want to, for the sake of time, I'm just going to introduce or illustrate a classification tree that can be used to classify a binary outcome. So let me walk you through how we can read this tree. So this tree would first decide, so if we want to classify a population or someone, then this tree would first ask the question, does this patient have a BMI over 32 or not? If this person does have a BMI over 32, then we go to the right branch. And we ask the second question, and then we ask the second question, does this person routinely consume soda or not? If the answer is also yes, then we will classify this patient as being diabetic, and vice versa for the other branches. So what you might have noticed is that this decision tree makes the final classification based on only 4 covariates. The first one is BMI, the second one is age, the third one is physical activity level, and the third one is routine soda consumption. However, this tree could have been fit against a data that contains tens and thousands of variates. So the question is, why does the tree pick these 4 covariates as your predictor? And also for a continuous variables like BMI, why does this tree pick an arbitrary cutoff point at 32 at the top of the tree? So to understand this question, we first want to note that those with BMI of over 32 don't all have diabetes. So some of them don't. So dividing people by BMI of 32 may misclassify a few patients. So to answer this question, the way the tree grows is that it will consider all combination of variables and cut points at each node, and they will select the best combination of variable and cut point so that the classification is lowest at each splits. It works slightly differently for regression tree, but the concept is the same. So in theory, this tree can grow infinitively until each node at the leaf at the bottom has only one observation. So the next question is, so when does the tree stop splitting and growing? So what distinguishes decision trees or different decision tree algorithm is how they can prune a complex tree back to a simpler tree, and also how we can preset a stopping criteria to prevent a tree from growing infinitively. Okay, so there are pros and cons to decision tree. So decision tree is known for its interpretability, and it's also very flexible to nonlinearity and variable interactions. And it also does not require data distribution assumptions. However, there are a few drawbacks. So decision tree is very sensitive to small changes in data. And in fact, small changes in data can create or lead to very different trees. In addition, decision tree can be very prone to overfitting, meaning that the model will extract noise as if it represents a true underlying model structure that we are trying to discover. So as I said earlier, due to the simplicity and interpretability of decision tree, it is a very popular clinical prediction tools for both diagnosis and prognosis. So this is just an example to show one application of decision tree. So this work is done by Katie Goodman, who is a PhD student in the Epi department. And so just want to point out, she predicted the likelihood that an infection is drug resistant or not while awaiting for microbiological confirmation. So ESBL infection tends to be, ESBL infection tends to be antibiotic resistant. So the way that this tree works is that it first asks patient, do you have a history of ESBL infection in the prior 6 months? If the answer is no, then the next question is, have you been hospitalized for over a night in an ESBL high burden region in the past 6 months? If the answer is also no, then the likelihood that this infection is drug resistant is only 7%. So that's how this tree works in this particular application. Okay, so next let's go into support vector machine. So support vector machine is also a supervised learning method, and it's also discriminative in nature. It constructs an optimal boundary called hyperplane to divide data into different classes. But when data cannot be divided based on just the raw data values, it transforms your data using mathematical function called kernel functions so they can be divided. So just graphically, what it means is that, so we said SVM construct an optimal boundary to classify observation. So going back to the same example that Justin introduced earlier, so if we want to classify patients into 2 groups, diabetic versus non-diabetic, based on just one covariates, for example, BMI, then this boundary is a dot. Based on 2 covariates, for example, BMI and age, then this boundary is a line. If we want to classify patients based on 3 covariates, for example, BMI, age, and sex, then this boundary is a plane, essentially. However, not all observations can be separated perfectly. So, for example, if this figure represents your age and BMI distribution in your data set, then we won't be able to find a single line to almost perfectly separate the black dots from the gray dots. But what we can do is to perform a simple data transformation and add 1 dimension to the data set based on this simple calculation. So again, this is a toy example, but the takeaway is that SVM can perform this type of data transformation using mathematical functions or other more complicated functions called kernel functions so that data can be separated in a higher dimension. So SVN also has its pros and cons. SVN does have reasonable interpretability, and it scales really well to high dimensional data set, and meaning data set with many variables. But the drawback is that we have to pre-select the optimal kernel function to use to make such data transformation. So there are different. Well, the optimal kernel function to make data transformation is not always obvious depending on how complex your data is. So one common practice is to apply cross-validation to a set of commonly used kernel functions and pick the one that works the best. However, this approach can be very, very time-consuming, and it does not guarantee that the set of standard kernel functions that you choose would include the optimal function. And the other drawback is that we have to use pairwise comparison for multiple classification because SVM is traditionally used for binary classification. Okay, so just one quick example. So because SVM scales really well with high dimensional data set, it is able to process large volume and content embedded in a data set like Twitter data. So in this example, this group predicts the level of influenza illness from Twitter data. And the figure on the right side compares the estimated influenza value obtained by this algorithm and compare it with the IOI values reported by the CDC. So the reported value is in gray and the estimate value is in orange, and it shows that the predictions are fairly accurate with an average error of only 0.28%. And well, this figure doesn't show temporality, but this paper conclude that this analysis is able to predict the IOI values 1 to 2 weeks before official CDC report becomes available. Okay, so next one is naive Bayes. Naive Bayes is supervised learning method, and it's the only generative algorithm that we're going to discuss today. So Naive Bayes predicts class membership by comparing probability of class membership given the data, and it has its foundation in Bayes' rule. So essentially, it fits probability of your observation given a known class membership by naively assume that your predicted variables are independent from each other. So, okay, so just to illustrate this concept graphically. So again, Naive Bayes would Naive Bayes classifier would calculate the probability of your class membership given your data, and then select the class, either diabetic or non-diabetic, based on whichever one generates a higher probability. And this value depends on two factors. It's actually a normalized product of two factors. The first one being the probability of observations produced under each class. So this is your likelihood function. And so because Naive Bayes assumes covariates are independent from each other, so it's essentially just a product of distribution of each of these covariates. And the second factor is the probability of class assignment. So this is your prior. It typically reflects your belief of the prevalence of the outcome in a population, either based on the study itself or from other published literature. Wrong side. Okay, so again, Naive Bayes also has its pros and cons. Naive Bayes can require a lot fewer parameters and smaller training set to train the algorithm, and it's also very robust to noise, missing data, mislabeled data, and irrelevant variables. But the problem is that the independent assumption is often violated. So going back to the same example of classifying your diabetes status based on, say, BMI and physical activities, is it really true that your level of BMI is independent from your level of physical activity? Depending on your population, this might not always be true. And one thing to note is that we can never interpret Naive Bayes probability as the actual probability of class membership. It's just a way to compare different classes and see which one is more likely to be the correct class. And when the data are correlated, Naive Bayes gives more influence to the likelihood function of the highly correlated feature in your data, and this may bias the prediction. But the good news is that as long as it's biased in the right direction, it's not going to affect which class that this classifier classify the observations into. Okay, so this is one application of Naive Bayes. So Naive Bayes has been used for risk prediction using censored time-to-event data from electronic health record. So electronic health record provides an alternative tool to longitudinal data sets for constructing risk models. So this figure compares two different tools in predicting 5-year. This figure compares two different tools in predicting 5-year risk of simulated clinical outcome in a data set with a lot of missing data. So here, dots represent the true simulated risk, and which is modeled using age and systolic blood pressure and the interaction of these two variables. We can see that the outcome and the age has a very non-linear relationship with each other. And the dashed line, which is the line that doesn't really predict the relationship well, is outcome from Cox proportional hazard. And the dotted line, which is right here, is estimation or prediction from Naive Bayes, and it captures the non-linear relationship between the outcome and age a lot better. Okay, so this is artificial neural network is the last supervised learning method we're going to introduce today. So artificial neural network is also a supervised learning method, and it's discriminative in nature. So it's essentially a group of computational models based on structure and function of biological neural network. And it consists of layers of connected neurons where connections are weighted. Artificial neural network learn by repeatedly comparing the output a network produces with the true output that it intends to produce. And then it modifies the weights, these weights between connections based on the difference that's calculated accordingly. Okay, so just visually, just to reiterate again, artificial neural network is inspired by the signaling behavior of biological neural networks in the brain. Neural network in the brain is a population of neurons interconnected through a complex signaling pathway to carry out a specific function when it's activated. Artificial neural network does the same by analyzing a complex interaction of your measurable independent variables in order to predict an outcome. So this is an example of a simple artificial neural network. So this network consists of multiple layers of neurons, and these layers are grouped into an input. These neurons are grouped into an input layer, one output layer, one hidden layer, and one output layer. So the 5 neurons in the input layers correspond to the 5 independent variables that you are interested in to use to predict diabetes status, which is the outcome here. And they are what we observed and what's measurable in your data set. And neurons in the hidden layers are not something that you can measure, but it represents a complex interaction of your independent variables. So each neuron takes inputs from the previous layer and produce output for the subsequent layer. But the question is, how do these neurons in different layers communicate? So the way it works is that each neuron calculates a weighted sum of its multiple inputs, and then apply the weighted sum of the inputs to an activation function. So when a weighted sum exceeds a certain threshold, then output. Then the neuron fires, and the output provides input for a subsequent neuron. So just to help relate it to statistical models, so essentially artificial neurons are a series of weighted regression, and the weights are somewhat analogous to the coefficients in your regression. So artificial neural network learns by iteratively assessing predictive error as signal propagates through the network, and then it updates these weights accordingly as signal propagates back through the network. Okay, so pros and cons of artificial neural network. Artificial neural network is very flexible to nonlinearities and variable interactions, and again, it does not require data distribution assumptions. It's one of the most actively developed algorithms in the field because it attracts a lot of interest. But the downside is its lack of transparency. As I showed earlier, all the interactions that epidemiologists could be interested in are effects mediated through the hidden layers, and these are something that we cannot observe in the output. And it's not super friendly to people who just started using machine learning algorithm because the training and tuning parameter requires a lot of expertise. And if we want to train a really deep artificial neural network, which is essentially deep learning network, and it requires large data set to achieve optimal model performance. So artificial neural network has been applied to develop individualized medication dosing strategy that evolve as a patient's clinical phenotype changes. So heparin is an anticoagulant. So overdose or underdose patients with heparin can lead to either bleeding or stroke. So this figure compares, sorry for missing the figure legend, but this figure compares patients' outcome in instances where heparin was administered based on a recommendation following the artificial neural network output, which is this red line, with recommendation that does not follow the output of artificial neural network. And basically, this is showing that following the recommendation of artificial neural network results is produce the best long-term performance comparing to other methods. Okay, so just going back to the slides earlier, just want to point out that artificial neural network is the basis of deep learning, and deep learning is essentially a multi-layer artificial neural network. Okay, so I know it's a lot of information. Hope everyone is following. So next we're going to talk about k-means clustering, which is an unsupervised learning method. It classifies observations into a pre-specified number of distinct clusters and works similarly as latent class analysis or principal component analysis. The way it works is that it randomly assigns centroid, its location, one for each cluster first, and then iteratively updates the centroid's location until classification remains unchanged. So what it means graphically is that, okay, if we go back to the same example and we want to partition group of study participants into two groups, one diabetic, one is non-diabetic, based on just their age and BMI distribution without knowing their actual status, then k-means is one of the techniques that we can use. So first we randomly select two centroids and drop it in a data set, and then we assign each observation to its nearest centroid. So the dots closer to the centroid will be assigned black, the color black, and the dots closer to the gray box will be assigned the color gray. And then it calculates the mean of the black dots and the mean of the gray dots, and then update the location of the two centroid. So k-means would repeat step 3 and step 4 repeatedly until the classification remains unchanged or the centroid stabilizes. So k-means clustering is very simple and easy to interpret, and it's very computationally efficient. However, we do need to decide a priori how many groups we want to classify the data into. So one common method is to run the k-means clustering algorithm for a range of k-values and pick the one that performs the best. And there are different ways that can help decide which k we choose, but the problem is that different methods don't always agree with each other. And in addition, k-means clustering assume variance within cluster to be the same. So if some clusters are much larger than the others, k-means can produce very non-intuitive results. So in this example here, most of us will classify the group, like the observations, into two groups, the one big cluster and one small cluster. But because of this assumption, the within cluster variance assumption, k-means clustering would assign some of the gray dots on the lower half level of the bigger cluster to be in the small cluster. So this is work done by Megan Wallace, who is also a PhD student in the Epi department, and she used k-means cluster to identify clusters of counties with similar socio-demographic characteristics. And this is particularly useful for comparing outcomes of health interventions because now counties in the cluster that share similar socio-demographic characteristics can serve as proper comparison groups when we want to compare, say, intervention outcome in a particular county with intervention outcome in a county with similar characteristics. So this is just a map of the k-means clustering outcome, showing how different counties are grouped into different clusters. Okay, so we talked about five individual machine learning algorithm, and so here we want to talk about the ensemble approaches. So single models are very prone to overfitting because, meaning that the model can be too closely fitted to the training data and leading to poor prediction performance, and also requires model assumption. So the way that ensemble approaches work is that it utilizes information from multiple models to improve predictive performance. So the idea behind it is that even though any individual model within your ensemble is not adequate to capture the entire phenomenon that you're trying to model, as long as each model, it performs better than random. So once we combine them, their predictive performance can improve significantly. So I just want to illustrate the legend first. So here the gray, the boxes represents your data, the arrows represents your algorithm, and the circles represent the classifier that's produced. So there are two broad approach that ensemble methods use to improve model performance. So the first one is to train the same algorithm. Is this working? So the first is train the same algorithm against different subsets of your original data. The second approach is to train different algorithm against the same original data set. So I'm going to go into each in a little bit. So ensemble approach 1 first. So this approach mostly tries to tackle the overfitting problem. So bagging and boosting are two methods that fall in this category. So both bagging and boosting train the same algorithm to different copies of the original data set. But bagging works in a parallel fashion and boosting works in a sequential fashion. So what it means is that bagging would first create bootstrapped copy of the original data set and then produce one parameterized output per bootstrapped copy. And the final prediction for a quantitative outcome is obtained by averaging the prediction from these classifier, and for a qualitative outcome, then the final prediction would take the majority vote among the classifier that's produced. So in boosting, it works a little bit differently. Here, initially boosting, the observations is initially given the same weight, but as model is trained against different copies of the data set, the weights will be updated. So the observations that's being previously misclassified will be given a higher weight. And the way that the final model combines the classifier is also different. And the model that shows low predictive accuracy will be given a lower weight in the final model. And the model that shows higher predictive accuracy will be given a higher weight in the final model when we combine prediction from these classifiers. And just want to mention that when the classifier are decision trees, so bagging algorithm essentially is called random forest. It's one of the most popular or well-known ensemble methods out there. Okay, so the second approach, both Bayesian model averaging and superlearner falls under the second approach. They both applies a range of different models to the same data set. But the way they weigh the candidate learner is different. So for Bayesian model averaging, the initial set of candidate learner is weighted by how much the data supports each competing model. The way the superlearner works is that it uses V-fold cross-validation or K-fold cross-validation to select weights to combine the initial set of candidate learners. So the way it works for Bayesian model averaging is that it first applies a range of statistical model to the same original data set. And then with each model, it calculates the model's specific estimates of the parameter of interest, which is in the oval shaped boxes here. And then these estimates are weighted by how much data supports each competing model, which is the boxes right here. And the final model produces a probability of effect size given a data, and it's essentially a weighted sum of these two components. So again, a superlearner is also an ensemble approach. It also considers a group of single algorithm. So the main feature of superlearner is that how much weights each candidate learner is given in the final model is determined by the prediction performance from each candidate learner. So I apologize if the font is a bit small, but the way it works is that superlearner will first split the models, split your data into V different blocks. and it will leave one segment out first, and then train each learner that's considered in the ensemble against the rest, the V-1 segments of your original data set. And then it predicts the performance, the performance of each trained learner using a segment that's held out. And then they do that for each held out version of the original data set. And then the prediction performance from the held out version will determine how much weight each learner is given in a final model. Okay, so this concludes the ensemble section. So now we go into the application of epi research. So we grouped the application of machine learning methods in epidemiology research into 6 different categories. So the first one is causal inference. Next one is text mining. The third one is clinical decision support tool. We'll also talk about geospatial application, prediction and forecasting of infectious disease, and GWAS. But for the sake of time, we're just going to leave out the clinical application for clinical decision support tools and application in analyzing GWAS studies. So let's start with causal inference. So relative to like the classical statistical or epi approaches, machine learning has historically placed less emphasis on causal effect estimation. Indeed, machine learning has been described as a black box method because it is hard to draw etiological inference from some of the machine learning algorithm, for example, artificial neural network. However, machine learning does offer important and arguably underappreciated tools for estimating causal effects in observational studies. So propensity score weighting is a common approach for estimating causal effects in observational studies. And it's traditionally estimated using regression methods, but when assumptions is unmet, it can render very biased estimates. Machine learning, however, implicitly deal with interactions and nonlinearities, and we hope we've also convinced you that they also performs really well in high-dimensional data sets. Machine learning does suffer problems with its interpretability, but for propensity score, it's not a huge issue. So like interpretability is not pertinent to propensity score estimation. And there are a lot of studies that have empirically demonstrated bias reduction, where propensity scores are generated with machine learning algorithms. So here's one example of applying machine learning algorithm to propensity score weighting. So we know that propensity score weighting is very sensitive to outlying weights. So this study tries to understand, can trimming large weights improve performance of propensity score weighting, and whether the benefits differ by propensity score estimation methods. So here on the right side, the y-axis is your bias in estimated treatment effects. So the lower the bias, the lower the value, the smaller the bias is. So what this is showing is that if we trim the weights produced by logistic regression at the approximately 85 percentile, then that reduced bias the most. And so the takeaway is that the 2 ensemble approaches that used here for estimating propensity score weights, the random forest and boosted cart methods, so these 2 lines consistently performs better than a single algorithm, which is the cart method right here. Okay, so next one is text mining. So the goal of text mining is to process textual information to discover patterns and connections in your records or like medical records. The large amount of electronic medical records out there provide valuable resource to improve health quality, promote clinical and research initiatives, and also reduce costs. But the sheer amount of information out there makes it impossible or infeasible for humans to perform manual extraction of the records, but machine learning is well suited for this task. So just a few examples of the utilities of text mining algorithm. So first of all, it's able to extract clinical information, And it can also be used to de-identify personal health information so that the de-identified records can be made public for research purpose without obtaining individual informed consent. And then it can also be very useful for subject recruitment because it can help identify patients who may qualify and benefit from participation in clinical research. And it can also help improve efficiency of systematic reviews by rapidly categorizing, identifying, and summarizing relevant literature. And it can also help supplement manual surveillance of infectious disease and other chronic diseases to speed up outbreak response. So this study reported on the use of electronic medical records that's currently in place in Mayo Clinic for prospective recruitment of patients with heart failure. And this study validated the naive Bayes algorithm as an approach to identify those with and without heart failure. So the outcome here is essentially heart failure, and the predictors or your independent variables are words in your clinical in the clinical notes. So naive Bayes here categorized the patients based on his or her record by calculating the likelihood of heart failure, the outcome, based on the co-occurrence frequency of the predictor, which is the words in your medical record. And this table compare the output from the naive Bayes with manual extraction of the data and shows a positive predicted value of 82%. All right, so text mining has also been incorporated into infectious disease surveillance, and this is a cropped image from the HealthMap website. So HealthMap graphically displays areas where disease are circulating. It is an automated infectious disease surveillance system that acquires and classifies and processes web accessible data. And it combines search query data, social media data, and also validated official reports and expert curated accounts such as PubMed. So these algorithms are designed to improve the detection of early outbreaks, and it can complement traditional surveillance efforts performed by international organizations or local government or local health departments. So geospatial application. So there is an ongoing need for getting consistent subnational scale data on demographics and disease burden. However, this could be a huge challenge in areas without well-documented census, surveillance system, or vital registration system. However, we've seen a lot of development in the field thanks to the growth in computing power and also availability of remote sensing data. And a lot of the new projects out there incorporate machine learning because of its ability to efficiently process high-dimensional data sets from various contexts and various geographic scales. So this is one example. So WorldPop project is an open source archive of demographic parameters on fine spatial scale. A lot of us use that for our daily research. It essentially uses random forest model, which is an ensemble model, to map global population distribution on a per pixel scale by combining a wide variety of geospatial covariates, including census surveys, satellite images, and cell phone data, among others, at the level of an administrative unit. And it provides, and then the model outputs information on population distribution at the grid cell level. And another example, so this is another example of geospatial application of ensemble models. So this study maps the dengue occurrence across the globe with the standard procedure. So they fitted a boosted regression tree model, which is also ensemble model, against two main data sources. The first one being the known or proposed environmental and socioeconomic covariates. The second one is expert consensus regarding whether dengue is circulating in a region or not. So the final model predicts the infection probabilities of dengue on a per pixel scale. So this group has produced disease burden estimates for a bunch of diseases, including dengue, which is in the picture here, and also Zika and Ebola. All right, so this is the last one, prediction and forecasting of infectious disease. So ensemble approaches are particularly powerful in predicting and forecasting course of an outbreak because it can account for uncertainties in your estimates over time as the data is trained, as the model is trained against the data, despite limitations in your data. And these limitations can include reporting delays or reporting in the surveillance data. And ensemble model is also able to it's also very good at integrating different data streams, including census, surveys, or like climate data, and it's able to process like very non-traditional data sources, including Twitters or remote sensing data. So this is another example, is one example of using ensemble models to forecast seasonal influenza outbreak. So this study, well, the takeaway is that this study shows it is advantageous to combine information from multiple flu activity predictors, meaning, so the examples that they gave is Google searches, Twitter microblogs, or hospital visit records and surveillance. This figure is showing that the best fitting ensemble approaches, which is in red, can track CDC's influenza report pretty well, like 2 weeks before the official report is released. Okay, so you want to talk about recommendations and resources?
Yeah, so thanks everybody for their time. I know that was a lot to go. We went through really quick. Stay up here, we're going to answer questions and stuff. That was a lot to go through really quick. And just to finish with some just recommendations for people wanting to try to incorporate machine learning algorithms into their work and pointing to you to a few resources. This will be relatively quick. So our first recommendation is to start with ensemble-based approaches, particularly good, I think, are random forest or superlearner. And the reasons is they're less susceptible to overfitting and they're less sensitive to tuning. A lot of these algorithms, neural networks, and I think decision tree algorithms, particularly non-CART decision tree algorithms in particular, can be black magic. You can, spend. It seems like you just need to have years of experience and expertise to know how to tweak the little parameters. Google can make AlphaGo be, the best Go player in the world, but nobody else can, right? So so these ensemble-based approaches tend to, they still have their own tuning issues, and they still, if you muck with stuff just right, you can cause overfitting. But they're a lot less sensitive to that, and it's a lot more likely to have valid results out of the box. And then to think carefully about validation. These models are so flexible that any common measure of fit or approach to thinking about fitting that that you might use it's going to do perfect on them, or can do perfect on them. They're really flexible. So you want to move from an idea of, instead of assessing model fit of the final model, to a cross-validation approach in almost all of your assessments of how well things are working. And the way we usually sort of the engineering approach to doing this is you sort of validate the approach and then make your final model. So you go and do a cross-validation where maybe you hold each observation out, maybe you hold 10% at a time, and do that to make sure things are working and your modeling approach is working. And then when you have your sort of expected performance, you finally fit to the entire data set to get your final, I'm going to put this out into the world model. And it's important when doing this to make sure you're validating the whole process. So you can't do, say, a variable selection phase and then the fitting phase, and then only do your cross-validation on the fitting phase. That's not really giving a sense of how things are working. And then think about the goal. A lot of these algorithms are great for prediction, and they've been developed, and developed and focused on giving good prediction and classification in particular settings. But that's not always the goal. Like sometimes causal interpretation is the goal. So, causal inference is the goal, or measuring exposure effect is the goal, or interpretation is the goal. And some of these algorithms, in particular, things like deep neural networks, are not suitable without a lot of extra framework around it. But along that, what we've presented here is just the tip of the iceberg of some of the basic algorithms and approaches to using them, and it's a very active research area and a very fast-moving research area. Along the lines of resources we have, as we've finished, like a lot of the content that we've talked about here is in a primer on basic machine learning primer for epidemiologists that hopefully will be soon to appear in AJE. We have some copies of the draft here for anyone who wants them. There's a ton of online resources, and courses on this. I think some particularly good ones is an introduction to statistical learning it's a nice text there's an online course that Stanford has developed to go along with it. There's a lot of courses on Coursera, edX, and DataCamp. This one on DataCamp on tutorial on machine learning in R is nice. It goes over an algorithm we didn't talk about here, k-nearest neighbors, but it's a good way to it's a very hand-holdy step-by-step walkthrough to get your feet wet. So sort of getting an idea more about applications, it just turned out, I think like this Monday maybe, PLOS Medicine just came out with a special issue on machine learning. So it's more focused on the diagnostic side. It's not that focused on the epidemiological side, but I think it has some interesting both discussions of use in the field and examples. And then there's a lot of optimized languages and packages out there, such as TensorFlow, that make some of this process easier, but also sort of step away from maybe the interface and the statistical techniques and the common packages that you might be used to using. So that's it, and we're happy to take any questions. Or we can all go eat lunch. Yes. Oh, sorry, you're in the dark over there.
So, are any of these approaches become something like linear regression? Anyone, like someone who studies statistics for 1 year, has a clear, a relatively simple, clear study design. Someone who has a simple study design and has learned just a little bit of statistics can use simple linear regression without making too many errors. They have to do a few check boxes of what diagnostics they have to do. Are there any, is there any research that you think that machine learning will be used for simple research, not big data? And are any of these resources useful, or is it only for the advanced?
So I think I do think the resources are very useful in a couple of different ways for simple work. I mean, some of the simpler algorithms that have their statistical counterparts, like decision trees, I think are quite useful if that's what if a classification type tree or algorithm or typical classification tree is something you use, and they're very simple to use. I think in terms of predictive accuracy, something if you need predictive accuracy and want to get sort of an upper limit of how well, you have a data set. So this is one way, and we didn't talk about much, this is one way I think these algorithms are often useful. So you have a data set and you have a huge number of covariates, right? And you sort of, you want to work with your, develop your logistic regression or whatever algorithm and know how well that works. But you sort of want to know what information in all of this data is there, like how well something could potentially work. So you can do something like take a random forest algorithm or super learner algorithm, an algorithm that gives a close to as good as you're going to get model, can get modeled for predictive accuracy out of the box. Fit it to your data with a lot of covariates, and that would give you a measure like an ROC curve or some other measure of like, this is how well you can do in predictive accuracy. And then you can go and say, okay, now I have my simple model that I'm going to have a causal interpretation of, and compare that to that, or that is more interpretable, and compare that to that, and have an understanding of, okay, how well, you know, I'm using the machine learning as sort of to develop a baseline. And also, some of these algorithms, particularly random forest, can help you identify things that are important predictors that are maybe, you know, can be part of a systematic way to select variables for further, more detailed consideration. So I think those are the, so I think those approaches are good. And then also for forecast, you know, are good for common use. And then I think the ensemble approaches for forecasts, for things that have to do with forecasting and prediction, the ensemble approaches more generally, I think are quite useful and generally the way to go, and don't only have to have some of the more, you know, like as we sort of alluded to at the beginning, this distinction between machine learning and statistical is somewhat arbitrary. But you know, the more statistical algorithms and the more machine learning, you know, style algorithms can all benefit from ensemble approaches if prediction and forecasting is the goal. So. Yes.
For example, if I were to, using machine learning for propensity scores, if I were to look through journals, would that be one of the acceptable things people are using it?
It's becoming increasingly used, and a part of and they seem to be more stable. It's becoming increasingly used, and they seem to be more stable. So that earlier figure that, you know, we talked about, I think it maybe was not completely clear what that was showing, is that, you know, the logistic regression approaches and stuff under certain conditions are unstable if you don't trim, right? So it can actually increase the error, or you can have increases in error from those approaches by, you know, if you don't do weight trimming, and of course you don't know how much of the weights, like this, trimming to 90%, that's kind of a rule of thumb in some cases, but you don't actually know where to trim your propensity scores ahead of time. That's a guess. And the machine learning approaches don't require the trimming. They have the same performance without weight trimming. Particularly the ensemble methods, because they're less, you know, sensitive to some of these collinearities and stuff. And I think increasingly, for that purpose, those algorithms are being used because interpretability is not an issue.
I had two questions. One is, are there any reporting guidelines for use of machine learning for manuscripts? And also, does Stata do all these as well, or is one better off using R?
There's definitely more implementations in R. I think most of the algorithms we've mentioned have a Stata implementation. I don't know if artificial neural networks do. Does artificial neural networks have one? Yeah, I don't. What?
I don't think even CART is available.
I think.
Yeah,
I think CART is available. But anyway, we have a list of the packages in the primer. We have a list for Stata, for SAS, for everything. What package in R? What packages implement these? So we'll just refer you to that. I'd have to go check. But yeah, and then in terms of reporting guidelines, I think you know, in the community I came from, right, you just made your code available. And I think that's increasingly the way everything is going. One thing is that, you know, a lot of these algorithms, particularly those based on cross-validation, are not going to get exactly the same result every time. But this is increasingly true for some statistical algorithms you're using too. There would be slight variations. But beyond that, I don't know of anyone who's published any specific reporting guidelines. I would say they mostly, for the most part, the reporting can fall under the same guidelines as your general statistical algorithms. The only difference being the measure of model fit has to be based on the cross-validation, needs to be based on cross-validation. Yes?
Yeah, I recently saw a presentation on using the LAPSO method, I think to predict PrEP diagnosis. I was wondering just kind of where that stands in terms of like the strengths and weaknesses. Lasso has,
the advantage of it is really analogous to, more traditional, traditional statistical techniques. It gets grouped, I think, it's one of those ones that's sometimes grouped in the statistical box, sometimes grouped in the machine learning box. The advantage of Lasso is that it, gives a regression model that, you can interpret, that can be interpreted classically. At the end, I think, and it does the variable selection in a more principled manner than some of the older techniques that people would use, like stepwise adding or removing covariates. I think there is some tuning in Lasso that sort of, and some interpretation in Lasso in terms of what to do that can be easily swept under the covers. But I would say it's a certainly more interpretable algorithm. It tends to have, because it's going for parsimonious model, it tends to not have the same, something like neural networks or superlearning or something is just like a grinder on getting good predictions. Right, that's what it does, and it doesn't. It's going to use all the information, and it doesn't matter if that's confounded or, whatever, because you don't care about that, right? You don't care if you're accidentally saying matches cause cancer because all you want to do is predict cancer. You don't care that the matches actually cause cancer, right? Whereas Lasso, you're generally trying. I think when you use Lasso, most people I feel are generally trying to get a model that would have more of a classical interpretation. So you have to be careful in that sense. Anything else? I guess I thought people are trying to get in here, though I thought we had till 1:30, but okay. Anything else? Any other questions?
Where is the primer?
We have a rough draft of it here. Note that it's still under peer review, so we'll have to get a peer-reviewed version. But we brought some copies in case anybody wanted them.